let's discuss about a different kind of an autoencoder. So it's called like variational autoencoder. Okay, so it is also called as VAE. So whereas autoencoder, we can call it as AE as a short. So okay, taking this. So what is the difference between like autoencoder and this autoencoder is very slight difference. Here it tries to learn the distribution of training data. So in the sense, previously what happened is, let's say, even there as well, but here we, let's say, so this is your values, right? So here we have, let's say, x. Here we are trying to reconstruct x tilde, and here is where we have, let's call it as z. Okay, so here in autoencoder we have this as a value, right? So we are trying to get a value. So indirectly, this, let's say these are the connections. Okay, I'm just drawing it this way. So the indirectly what it is trying is, so it tries to learn the features from it. Okay, so and this indirectly is your training data. It tries to learn the distribution of your training data. But here these are the values. So something like, let me give an example. If you take an image, okay, so image of a person. Let's say if you give an image of a person, so what maybe it will try to take is what is a skin color. So is he wearing specs or not, spectacles, or what is hair color, maybe kind of is he smiling or not. So these such kind of outputs, like maybe it will try to get from here. Okay, some value here, some value here, some value here. So indirectly, like I'm not saying exactly these values, it will have its own representation, but just to kind of interpret, maybe it will have these kind of values. Okay, so is nose broad or not a broad, or broad nose or like a thin nose, is it long or not, or something like that. Okay, it can take these kind of things as a features, and maybe it will store a value here, right? So for each image you'll be getting some value. Skin color, like something like 0.5. So is spectacles, is he using like maybe 0. So maybe haircut, hair color, again like something, hairstyle, again like some feature for that. So something like that it may be extracted. This is just my interpretation. It is nothing actually it will be doing, like it will be doing something else. Okay, so we are unrepresenting with some value, and from that value it's just like a kind of describing like what your data is. We have a kind of latent, we call this as latent variables. Okay, latent variables. So kind of a descriptors to your data, and these descriptions, from this description you are again reconstructing your input. Okay, so this is what we do in autoencoder, right? So it just like in visually we see in movies and all, right? So like person who, in case like they draw a suspect photo, like try to draw a suspect photo based on a kind of description. He will ask like, how broad will be your eyes, like large or not, how, like the painter will ask questions, and like uh, like the person will be describing the suspect's features, and like he'll be trying to draw, right? So that such kind of thing happens in this level where we it is reconstructing, and this level it's encoding anyway, right? So it's like extracting some features out of it. So this is what is doing here. So but here what it should be is, this x and z should be in similar distribution, right? Because how you give your data, so your features will also be in similar distribution, right? So what you call is your probability of x given z, like we kind of represent it this way. So is similar to like like distribution of x is similar to distribution of z. So that is what we try to find out from here. Okay, so what we can do is, like in here it is just a value which it is taking, right? So instead of it, like variation autoencoders will try to get the distribution of the data. Instead of just a single value of the data, it tries to get a distribution of the data. So what it tries to do, let me so variation autoencoder, what it tries to do is, so let's say there are some values, so maybe add, like make it more large. So here, instead of your values, it tries to get a distribution of our data. That is what we are saying, right? So how actually will be the distribution? So distribution, we assume that like our input data is normal distribution. So even our Z, we assume that it is normal distribution. So and also we try like what distribution we are trying to learn, right? So this distribution we represent it by using like mean and variance, mean mu, variance mu sigma square. So this is what we need. Our standard deviation is sigma, right? So if we have these two values, we'll be getting the distribution, right? So what we try to do is get this kind of mu and sigma scale. From that we'll, like for let's say these are like features, we have three features, okay? So in that, these are three are for mean, these three are for variance. So what it tries to do is, it tries to get a mean 1, mean 2, mean 3. So actually there is this, again this reconstruction is there, I'm just not drawing it, I will draw it, no problem. So it try, if I'll draw it then, like as of now, let's see this. So variance 1, variance 2, and variance 3. Okay, it tries to get these information. From this, what we got, like we got three features which distributions, like one with distribution, like we represent this kind of notation for normal distribution with mean 1. Let me write it as mu1 sigma square, that will be easy. So what we try to get is mu1 sigma 1 square. Similarly, second is mu2 sigma 2 square. Similarly, mu3 sigma 3 square. So let's say we got these information from here. So what actually does this mean is, so previously we described, in case take the same example, previously we had something like this, right? So you took an image. Okay, from that image we try to have kind of a distribution. So skin color, hair color, tall, thin or fat, so something like this, right? So these kind of distributions we used to have a single value. Now it will try to learn a distribution out of it. Means previously where it is a single value, now it will try to learn a distribution with, this is the mean mu1. So and from this is sigma, right? So from this sigma you will calculate sigma square, right? Sigma, so from this you will be getting mu1 comma sigma 1 square. So with these two values you can draw this. So similarly for the second feature as well, you'll be getting some value. Okay, mu2 sigma 2 square. So third as well, fourth as well, like that. For what values you have, you'll be getting a kind of distribution instead of a single value. So that is what this variational autoencoder will learn. So once this is learned, so here it is mean and standard deviation, right? So from this, what we do is, so from this, we take a sample out of these values here. Okay, because we need to do reconstruction anyway. Like the concept is same overall. So where we also do a reconstruction from these values, finally get these values and say that this is your x, this is your x tilde, and take a difference between them. That is there, that is common. But instead of having a feature as normal values, we try to learn a distribution of your input data. Okay, so distribution of your features, distribution of your this thing. So and then like here these are mean and variance, right? So while like training, you need for reconstruction, we need a data from it. So what we do is, so instead of, we need a single values from each of them. So what we do is, from mean 1 and variance 1, which you have a kind of distribution like this, we sample a data point. Okay, that value will be here. Means sample in the sense there will be some value here. And maybe in the second distribution, we sample one more data point. In the third distribution, again, we sample one more data point. So those values are here. And these values, we pass it just like previously, what is there, right? So using that, we'll be passing and then getting your reconstructed output. So this is the only difference between your previous one and like actually this is newly added, like what you have this, right? So this is newly added. And then like apart from that, it is rest is all same as like autoencoder. So now what we do is, so this is a reconstruction, right? So we, from the values which we sample from these mean and variance, so this distribution, we get your features. So these features, we use it back again to for reconstruction of input. So what will be your loss? So just like your reconstruction error, so which will be x tilde minus x. So if this is fine, okay, but we also have to, here we are introducing something else, right? So as a mean and stand variance, so we also have a loss, like where we, because we are having some target here, what we are saying is this should learn the distribution of input, right? So here what we should be error is the difference in distribution of x comma z. So this is what we need here. Okay, here reconstruction error is clear, like how we can get. Similar, similarly, if you want to know the difference in distribution between two different values, means like you have a distribution like this, and you have one more distribution which is like this, where you have difference in mean and standard deviation. Such kind of scenario, if you want to know how similar are these two, so there is a measure from the for those which was like KL divergence. So divergence, so like in detail, like we'll go into KL divergence at different in different session. But what this do is, like this KL divergence will give is a kind of a measure between two different distribution. Okay, so you use this KL divergence function to get a different like deviation, how the distribution of input and how the distribution of that latent bottleneck layer here, right? So what is the distribution between those two? You calculate KL divergence for those. So that will be a kind of an error between those two. Okay, so how different are those two? So we give it also as a loss. So now we give it this to optimizer for update of weights. So now what will happen? It will try to reconstruct the output, as well as it also tries to reduce this, right? So it tries to reduce this. It means like your x tilde will be almost equal to x, and here it tries to reduce this as well. So for this, what will happen is it tries to get the distribution of x similar to distribution of z. So what it will do is it will try to learn this distribution here. So this mean and variance of the distribution, right? It tries to learn within the network, and that is where finally we achieve this mean and variance, the distribution of it learned the distribution of network, and also we are able to reconstruct. This is where we call, this is what we call variational autoencoder. Okay, rest all is similar, but this is what we call as a variational autoencoder. We have calculated loss here, like using reconstruction error and like KL divergence, right? So like while taking a loss and doing an optimization, like using back propagation, we may face a kind of a difficulty here, because we are calculating this z, what is a latent vector here, so using a random sample between your mean and variance, right? So like while going backwards for calculating gradients, what you will have is like you need to calculate z in terms of mu, as well as like z in terms of mu2, so on, like in terms of sigma as well, right? So how will you calculate this? You need some kind of relation between your mu and sigma with z, right? So but you don't find it here. So how will you do it is like we use a kind of a reparameterization trick, trick. So for getting a relation here, so instead of directly randomly sampling from your mu and sigma from your distribution, getting a z like point here to get z here. So instead of that, what we do is we will have introduce one more distribution, which is a normal distribution of mean 0 and standard deviation 1. And we what we have is z in terms of like mu plus like sigma in of epsilon. Let's say this is epsilon, and this epsilon value is randomly sampled by with this normal distribution of 0 to 1. Okay, so with this value we'll calculate a z, like it means indirectly we are shifting our mu our normal distribution by mean mu, and then also we are adding a standard deviation to it, like making a standard deviation scale by sigma. So now we get a relation this way, where z like from this distribution, now what we do is we randomly sample this epsilon based on our 0 to 1, and like normal distribution of 0 to which like mean is 0 and like standard deviation 1. From that value we sample some value. Okay, so that value we use it to calculate like and get a relation between like mu plus like sigma, using this product into this epsilon value. From this we finally get some value from it, right? So that value we use it as a jet. So now we'll be able to calculate like u by u and like z by dz by d sigma, right? So because now gradients are available, because we have a relation now, right? So from this we'll be able to calculate dz by d mu as well as dz by d sigma. So now we'll be able to do a back propagation, right? So now the rest of the things are same as like previous. So how we do is like the same thing, like you like have from the loss you calculate gradients going back further, like because now you have a relation between your mu and z. So and you calculate till input with this back propagation, you update the like using gradient descent algorithm, you can update the weights and then optimize your network. So this is how like actually variation autoencoders are done, and as those has been optimized for your specific problem. Okay, in the same example what we use, right, the anomaly detection. So this performs much better than like previous case, like where we have discussed about we have a fault signals, right? So sensor signals where sometimes it should identify the fault. Okay, something like this. So these will get identified when we can use by using variation autoencoders. So rest things are same as this, like rest of things are same as how what we have discussed during autoencoder, but only thing that differs is like instead of like we train the data with non-faulty data to variational autoencoder now for getting a reconstruction error, right? So what we do is in this variation autoencoder will learn what are the distribution of each of input, right? So here it learns how your values will be. Means like your sensor signals, right? So how your sensor signals will be, in what range will that be, what will be the mean and the standard deviation from it. Like that for each signal, like not actually signal, it will learn for each features what it will extract. So it will learn the mean and standard deviation for those, and from that data what it tries to do is, so it sees the distribution, right? So in case if there is any fault data coming over there, right? So this fault data doesn't come within this distribution. Okay, it doesn't come within this mean and standard deviation. So what it may be somewhere abnormal point here. So what it identifies is from this it will not able to reconstruct something within this which is of this kind, because it is not trained in that way, and the mean and variance, the distribution is not like this. It is, we only trained it for like this, we did not train for something like this. So here mean and variation will be different. So taking that into consideration here, so what it will happen is, so it won't be able to reconstruct. So as we it won't be able to reconstruct, so the reconstruction error will be more. be more for fault data. So in case if there is abnormal data, so it will be more. So from that we'll be able to identify where it is going wrong, right? So that like a fault which there is a fault over there. And in case if we pass non-faulty data, means like which is in this range, so here mu and standard deviation are within the same range. Okay, we are getting some point here, so this is okay, it will be able to reconstruct. Okay, so here reconstruction error is almost zero. So it's not an anomaly. So when your reconstruction is high, then we can say it, raise a flag and say it as an anomaly. So this is how it can be used. Okay, so this is about variational autoencoder and how this use cases, and we can also use the same in like many other cases. Like it can be a kind of a generation like of new faces, like we can do it. Means like you have your face and you want your same face how you look in like when you are kid, or when you look when how you want to know how you look like when you grow old, right? So you can do such kind of use cases again using this variational autoencoder as well. So even with autoencoder it is possible, but variational autoencoders gives much better performance in such kind of scenarios. Okay, so this is about variational autoencoder.